The rock is sitting on Mars right now. It's inside a sealed metal tube about the size of a piece of chalk. It was drilled out of a stone the rover team named Cheval Falls in the summer of 2024. The rock has small dark markings in it. The people who found them call them poppy seeds and leopard spots. On Earth, patterns like that would be a textbook signature of microbial life. Last September, after a year of careful review, NASA's official position became that the sample contains what they call a potential biosignature. They are extremely careful with the word potential. Nobody is saying life, not yet. But the tube is still there. It's sitting on the surface of a planet that died roughly 3.5 billion years ago. And the earliest we might get it home is somewhere in the late 2030s. We are going to talk about that rock tonight. But not only about that rock, because Mars is not the only dead world. It may not even be a rare one. What we are doing tonight is sitting with a question that does not get asked very often because it makes people uncomfortable. The universe, as far as we can currently see it, contains a confirmed inventory of just over 6,000 worlds beyond our solar system, and a credible estimate of hundreds of billions more in our galaxy alone. The natural assumption is that some fraction of those should be alive. Someone should be home. But the more we learn about what it actually takes to keep a world habitable, the more it starts to look like the real story is not about life starting. It is about life lasting. By the end of tonight, you are going to see the night sky a little differently, not as a place that is empty, as a place that might be very, very full of something quieter than we expected, something that already happened, something that ended. Here is where most people get the universe wrong. When they think about whether anyone is out there, they imagine two doors. Door one, the cosmos is teeming with company, and we just haven't run into them yet. Door two, the cosmos is empty, and we are alone here, and that is just how it is. Those are the two answers people argue about. There is a third door, and that is the one we are walking through tonight. It is the possibility that the universe is not empty and not full. It is the possibility that it is full of worlds where the conditions for life arrived and then left. Worlds where life may have started and then stopped. Worlds with the lights still on and nobody home. Before we go further, if you are finding yourself sitting with what was just said about that sealed tube on Mars, take a moment to like the video or subscribe. It genuinely helps this channel reach more people who actually want to think about this stuff at 3 in the morning instead of being yelled at about it. That is it. Now back to it. The number to sit with first is 6,087. That is the count of confirmed worlds outside our solar system as of January of 2026, listed in the NASA Exoplanet Archive, which is the official register where confirmed discoveries get logged. NASA crossed the 6,000 mark in September of 2025. To put that in scale, there are about 195 sovereign countries on Earth. We have more confirmed worlds beyond our solar system than we have countries here, by a factor of 30. And those are just the worlds we have actually managed to detect. The real number, the estimated number, is much larger. There are roughly 200 billion stars in the Milky Way. The working assumption, based on data from the Kepler and TESS missions, is that nearly every star has at least one planet. Some have many. So when astronomers do the arithmetic, they end up with somewhere in the hundreds of billions of planets in this galaxy alone. Of those, the latest estimates put the number of planets sitting in the habitable zone, the region around a star where liquid water could theoretically exist on the surface, somewhere in the tens of billions. That is a lot of worlds. So why is it so quiet? The first thing to understand is that habitable zone is a misleading term. It only means liquid water could exist there in principle. It does not mean water is there. It does not mean it ever was there. It does not mean the planet has an atmosphere capable of holding water. It does not mean the surface temperature is currently within liquid water's range. It just means the orbit sits at roughly the right distance from the star. So when you hear that there might be tens of billions of habitable zone planets in this galaxy, what is actually being said is that there are tens of billions of orbital slots where conditions are not ruled out. The conditions could still be ruled out by 1,000 other things, and very often are. Out of the 6,000 confirmed exoplanets we have, most of them are nothing like Earth. The first ones we found were hot Jupiters, gas giants so close to their stars that their atmospheres glow. They are the easiest to detect, which is why we found them first. Then came super-Earths, rocky worlds bigger than ours, often in orbits so tight that a year there lasts a few Earth days. Then came tidally locked planets, where one side of the world faces the star forever and the other side faces away forever, leaving a permanent sunlit hemisphere baked into rock and a permanent dark hemisphere frozen so cold the air can fall as snow. Then came planets in scorched orbits, planets with no atmosphere left, planets where the surface gravity is too high for a human heart to keep beating. When you look at the catalog of what we have actually found, the planets that resemble Earth in any meaningful way are rare. Out of 6,000 confirmed worlds, the number that could be described as roughly Earth-sized, in roughly the right orbit, around a roughly stable star, is in the low dozens. That number often confuses people. Low dozens sounds like a small, almost dismissive count, but it is important to understand why it is that small. The detection methods we rely on, primarily the transit method and the radial velocity method, are heavily biased toward finding large planets close to their stars. A Jupiter-sized world orbiting close to its star blocks a lot of light and produces a strong gravitational tug. An Earth-sized world in a wider orbit produces a much weaker signal. It is like trying to spot a single firefly in a stadium full of floodlights. The fireflies are there. They are just invisible to our current instruments. So, low dozens does not mean there are only low dozens of Earth-like worlds in the cosmos. It means that out of the tiny fraction of planets we have been able to detect, only a handful meet the minimum criteria for comparison. The rest are still hidden. The detection limits are the real story here. Our tools are not good enough yet. We are reading the library by the dim light of a single candle, making out the shapes of the biggest furniture in the room and calling that a complete inventory. The low dozens number is a statement about our telescopes, not about the universe. So part of the silence is just that. Most of these worlds were never going to talk to us in the first place. They could not. They do not have the chemistry, the temperature, the air, the time. They are stones in space. But that is only part of it. Because the truly strange thing is not the worlds that never could have been alive. The strange thing is the worlds that maybe could have been, the Earth-like candidates, Those are out there in real numbers, even by the most conservative estimates. And out of those, we have no signal, no radio call, no optical flash, no chemical fingerprint we can identify as life. Nothing. That is the silence that is hard to explain. The silence of the worlds that should, by any decent statistical argument, have something on them. There is an image I keep coming back to when I sit with this. The universe, at least the part we can see, is not quiet because nobody ever existed in it. It is quiet the way an old library is quiet. You walk in at night and the lights are off, but the building is still there. The shelves are still there. The books are still there. Every spine you pull off has a real author behind it. Real ink, real pages. The library was not built empty. Somebody filled it. But it has been a long time. The writers are gone. The readers are gone. The lamps overhead have burned out one by one. The building has gone quiet. The books are still there. The voices are not. When astronomers find a planet through the Kepler mission, what they actually see is a star that dims a little every few days or weeks in a regular pattern. The dim is the planet crossing in front of the star, blocking a fraction of its light. That is it. That is all we see for most of them. We never see the planet directly. We see a slight repeating shadow, and from that shadow, we work out how big the planet is, how close to its star it sits, how long its year lasts. We do not see what is there. We see that something is there, and then we go to the next star. That is what most of exoplanet science looks like. You stand outside the library. You can tell from the shape of the shadows on the wall that the building has shelves and aisles and corners. You can guess at the number of books. You can guess at their size, but you cannot go in. And what you mostly cannot do is tell from the outside whether anyone ever read them. The other thing to understand about the silence is the timing. Even if every Earth-like world out there had developed intelligent life, the odds of any two civilizations existing at the same moment in a galaxy whose history spans more than 10 billion years are slim. Human radio communication has been a thing for about 100 years. Recognizable human civilization, somewhere around 10,000. Anatomically modern humans, around 300,000. The Earth has been habitable for about 4 billion years. If you compress all of Earth's habitable history into a single calendar year, the entire span of human existence shows up in the last 90 seconds before midnight on December 31st. Modern science fits in the last second. Now picture a galaxy where every habitable world has its own version of that calendar, started at a different time, ending at a different time, with most of the calendar quiet and ordinary, and only a few seconds in each year where anything loud is happening. The chance of two of those calendars overlapping in those few loud seconds is small. Most of the time, you would reach into the universe at random, and you would pick a world that either had not started its civilization yet, or had finished it, or had never had one at all. Silence is not proof of empty. It is proof of timing. There is a phrase astronomers sometimes use, half joking, when they are talking about all of this. They call it the Great Quiet, not the Great Filter, which is a specific argument about what stops civilizations from growing. The Great Quiet is just the observation. It is just the listening. The fact that the receiver is on and the signal level is essentially zero and has been essentially zero for as long as we have been able to check. Some of that quiet might be that nobody is out there. Some of it is almost certainly that somebody was and is not anymore. The library, in other words, is real. The shelves are full, the lights are off. Whether anyone is still inside is a question we do not have a tool sharp enough to answer yet. What we do have is the shape of the building, and a sense, growing every year, of how many rooms it contains. If you want to know what one of those quiet rooms in the library looks like up close, we do not have to travel far. We already have one. It is the planet next door. Mars is the easiest dead world to talk about because we can see it. You can step outside on the right night, look up, find the small, steady reddish light in the constellation we happen to call wherever it is that month, and there it is. The fourth planet from the Sun, the next-door neighbor, the one you do not have to imagine because it is actually there. For most of human history, Mars was a wandering light in the sky and a name for a god of war. It became a place sometime in the late 1800s when telescopes got good enough to show that the reddish dot was a world with polar caps that grew and shrank with the seasons and dark patches that some astronomers convinced themselves were vegetation. By the late 1800s, the Italian astronomer Schiaparelli was reporting straight lines across the Martian surface, which the American astronomer Percival Lowell convinced himself were canals dug by a dying civilization to move the last of their water from the poles to the equator. None of that turned out to be true. The lines were an artifact of the eye trying to make sense of fuzzy images. The dark patches were dust and stone. There were no canals, but the idea of Mars as a dying world turned out to be closer to right than anyone realized. The Mars we have today is by any reasonable definition dead. The surface temperature averages about minus 63 degrees Celsius. That is roughly the coldest temperature ever recorded in Antarctica, except that on Mars, that is the average, not the extreme. The atmosphere is so thin that liquid water on the surface would boil and freeze almost at the same instant because the pressure is too low to keep water in its liquid state. Standing on the surface of Mars today with a perfect spacesuit, you would still feel the cold soak into the soles of your boots within minutes. The sky overhead would be a pale butterscotch color, not blue, because there is not enough air to scatter light the way Earth's atmosphere does. The sun, when you found it, would look smaller and dimmer. The horizon would feel close because Mars is a smaller world, and the curve of the ground falls away faster. It would feel like a place that something used to live in. That feeling, it turns out, is correct. Here is what we know. Mars used to have a magnetic field, a real one, a planet-wide one generated by a molten metal core spinning at the center of the world, the same way Earth's core spins now. That magnetic field acted as a shield. It deflected the solar wind, which is the constant stream of charged particles the sun throws off in every direction. The shield meant that whatever atmosphere Mars had, it could hold on to. The shield meant water on the surface could stay water. The shield meant a sky thick enough to feel like a sky. Then the shield went down. The current best estimate from paleomagnetic analysis of Martian meteorites and remote magnetic measurements of the crust is that Mars's global magnetic field collapsed roughly 3.9 billion years ago. That date has been pushed and pulled by different studies in the past few years. The most recent work, including a high-profile paper out of Harvard, published in 2023 and reaffirmed by follow-up studies through 2025, suggests the field may have lasted slightly longer than people used to think. But the headline is the same. The core cooled, the dynamo stopped, the shield went away. After that, the atmosphere started to bleed, slowly, not in one event. Over hundreds of millions of years, the solar wind picked at the top of Mars's atmosphere, knocking the lighter molecules off into space one at a time in a process so gradual that if you had been standing on the surface watching, you would not have noticed anything different from one century to the next. But the budget was negative. More air was leaving than was being replaced, and eventually the bank account ran out. Today, Mars's surface pressure is somewhere between 1 and 40 millibars, depending on altitude and season. Earth's surface pressure is 1,013 millibars, so Mars currently has less than 1% of the air pressure we have here. To find air that thin on Earth, you would have to go up to about 30 kilometers above the surface, which is about 3 times higher than a passenger jet flies. That is the kind of air Mars now has at ground level. But there was a window. There was a long window. And inside that window, things happened. The Curiosity rover, which landed in Gale Crater in 2012, has spent more than a decade slowly driving up the slopes of a mountain in the middle of that crater, examining the rocks layer by layer. Gale Crater was a lake. We know that now. The layered mudstones, the river-worn pebbles, the salt deposits, the clay minerals that only form in standing water. All of it tells a story. Around 3.8 billion years ago, this part of Mars was full of liquid water. There was a deep lake fed by rivers. The lake stayed for a long time. The mineral evidence suggests it persisted on and off for something like 700 million years, with the last clearly habitable conditions winking out somewhere around 3.1 billion years ago. 700 million years is a length of time that is hard to hold in your head. Life on Earth, in any complex form anyone could recognize, has only existed for about 600 million years. The Cambrian explosion, when animals with hard parts first showed up in the fossil record, was about 540 million years ago, which is to say, Mars's habitable window on the surface lasted longer than the entire history of complex animal life on Earth so far. And on Earth, in the same era, life had already gotten started. The earliest convincing evidence of microbial life on this planet shows up in rocks around 3.5 billion years old. And there are some hints, debated but real, of biological signatures going back maybe 3.8 or 3.9 billion years, which means that the two planets were running the same experiment at the same time. They had liquid water at the same time. They had atmospheres at the same time. One of them, we know for sure, started growing life. The other one had every ingredient to do the same thing. And then, somewhere around 3 billion years ago, the conditions on Mars stopped being friendly, which brings us back to the rock. The Perseverance rover landed in Jezero Crater in February of 2021. Jezero, like Gale, used to be a lake. You can see in the satellite imagery the fossilized remains of a river delta, where ancient water flowed in from the surrounding highlands and dropped its sediment in fan-shaped layers. Perseverance was sent there specifically to look for biosignatures. It has been driving across that delta, taking samples since it arrived. In July of 2024, Perseverance drilled into a rock the team named Cheval Falls. The drill produced a small cylindrical sample sealed in a metal tube. The team noticed something unusual right away. The rock contains small nodules, dark-colored, distributed through the sediment in patterns that on Earth would be unusual. Some looked like poppy seeds. Some looked like leopard spots. Chemical analysis done with the rover's instruments identified the nodules concentrations of iron phosphate in a mineral form called vivianite, along with iron sulfide in a mineral form called greigite. On Earth, that combination is interesting. Vivianite and greigite, together with organic carbon in mudstone in those kinds of patterns, are what gets produced by certain microbes when they do their chemistry. Specifically, when iron-breathing bacteria pull energy out of sediments by moving electrons around between iron and sulfur compounds. The patterns Perseverance saw in the rock it sampled are the kind of patterns a textbook would call a microbial biosignature. The paper describing the find was published in Nature in September of 2025 after a year of careful internal and external review. The authors are extremely careful with their language. The phrase they use is potential biosignature. They list the alternative explanations. The patterns could be produced by chemistry that is not biology, by certain volcanic processes, by water-rock interactions that do not involve life at all. They do not claim they found life on Mars. They claim they found something that on Earth would be the first thing you would point to as evidence of life, and that other explanations remain on the table. The sample is sitting on the surface of Mars right now in its sealed tube. The Mars sample return mission, which would bring it home for analysis in laboratory that can do tests no rover can, is in flux. The original schedule, which would have had the tube back on Earth in the early 2030s, is now under budget review and architectural change. The current best estimate for retrieval is somewhere in the late 2030s, possibly later, which means that the most consequential rock sample in the history of our species is going to sit on the surface of another planet for at least another decade waiting for us to come get it. In the meantime, all we have is the photograph. There is an old idea about photographs that they are not so much images of people as they are of moments. The person you photograph today will keep aging. The moment frozen on the film does not. So you end up holding in your hand a small rectangle that is a piece of time separated from the person it came from. That is what Cheval Falls is, a piece of time, maybe a piece of Martian time when something was alive. Maybe a piece of Martian time when no life was ever present, and the rocks just happened to assemble themselves into patterns that look like life would have made them. We do not know. The image is real. What it shows is still being worked out. If you have ever moved into a house that someone else used to live in, and you have gone up into the attic, you know the feeling. There is a box up there. The box has photos in it. Real photos, real people, real faces in clothes you do not recognize, in rooms you do not recognize, in places you have never been. You are holding pictures of people who walked through your hallway and ate in your kitchen generations before you bought the property. They are not your family. They are just people. The fact that they were there doing ordinary things in the same physical space you now live in is hard to absorb the first time you really notice it. Mars is like that attic. You climb up there expecting dust, expecting nothing, and instead you find a photo album. The pictures are real. They are of someone you have never met, and the camera that took them stopped working a very long time ago. That is the situation we are in with Mars. The rock in the tube is the latest photograph from the attic. There may be others. There almost certainly are. The Mars 2020 mission is one of dozens of missions, robotic and orbital, that have been studying this planet for 60 years. We have been knocking on the door for 60 years. Sometimes the door rattles. Sometimes a window opens. Mostly the house is quiet. The wind blows red dust against the porch. Mars's porch light is still on. We have been ringing the doorbell for 60 years. Mars is the obvious dead world, the one that is harder to think about because it is our actual twin. The one we do not usually let ourselves consider is the planet on the other side of us, the one we usually skip past in school, the one we file under hot rock and stop thinking about. That is Venus. We do not think about Venus the way we think about Mars. Mars gets all the cultural attention. Mars is the rover planet, the future colony planet, the one people put on the cover of magazines next to a square-jawed person in a spacesuit. Venus is the one we mostly skip. You learn about Venus in school for about a week. It is the one with the runaway greenhouse. It is the one that is too hot. The greenhouse gone wrong example. The lesson where the teacher tells you that is what happens if a planet gets too much carbon dioxide, and then you move on. That telling is wrong, or at least it is missing the important part. Venus, on paper, is Earth, almost exactly Earth. It has roughly the same diameter as our planet, the same mass, the same density. It formed at roughly the same time out of the same protoplanetary disk from the same general mix of materials. It sits inside the inner solar system. It is our sister world by every standard astronomers use to mean the term sister world. If you grabbed a stranger and showed them the basic specifications of two planets, one labeled Earth and one labeled Venus, and ask them which one supports life, they would have no way to tell. And here is the part that I genuinely think people should sit with for a minute. Venus may have been habitable with liquid water oceans on the surface for as long as 2 to 3 billion years. That is not a wild speculation. That is the conclusion of climate models run by NASA's Goddard Institute for Space Studies. The Way and Del Genio simulations, published originally in 2016 and refined in subsequent papers, take what we know about Venus's likely early conditions, run a three-dimensional climate model forward in time, and find that under reasonable assumptions about cloud cover and rotation, Venus could have had a stable temperate climate with surface oceans for somewhere between 2 and 3 billion years before it tipped into the state it is in now. 2 to 3 billion years. To put that in scale, life on Earth has been around in any complex form, anything more than single cells, for about 600 million years. Venus, on this timeline, had liquid surface oceans for longer than complex multicellular life has existed on Earth, 5 times as long, give or take. There was on the surface of that planet an environment that under any reasonable definition would have been habitable for an amount of time that dwarfs the existence of any animal anyone has ever named. Whether anything used that habitat is another question entirely. We have no fossils from Venus. We have at this point no surface samples from Venus. The few Soviet landers that touched down on the Venusian surface in the 1970s and early 1980s lasted on average less than 2 hours before the heat and pressure killed them. The longest survivor, Venera 13, lasted just over 2 hours. The pictures it sent back show a flat tan landscape of broken rock. The sky overhead, a heavy sulfurous yellow. No animals, no plants, definitely no civilizations. But the question is not whether anything is there now. The question is whether anything was there 2 billion years ago when the planet might have looked completely different. Then, somewhere around 700 million years ago, the conditions on Venus changed. The triggering event is debated. The leading candidates include a massive global resurfacing event where the entire surface of Venus was repaved by volcanic activity in a relatively short geological window, possibly within 50 to 100 million years. There is also the steady brightening of the Sun, which has been increasing in luminosity by roughly 10% every billion years over its life. There is the possibility of a runaway volcanic outgassing episode that pumped enormous amounts of carbon dioxide into the atmosphere over a relatively short time. There is a possibility that more than one of these things happened together and crossed the threshold. The climate system could no longer balance. Whatever the trigger was, the climate flipped. Water vapor, which is itself a powerful greenhouse gas, trapped more heat in the atmosphere. The hotter atmosphere held more water vapor, which trapped more heat. The oceans began to evaporate. The hotter the atmosphere got, the more the oceans evaporated. The more water vapor entered the atmosphere, the hotter the atmosphere got. That feedback loop is what scientists mean by a runaway greenhouse. By the time the runaway finished, Venus's oceans were entirely gone. The water vapor in the upper atmosphere got broken apart by solar ultraviolet radiation. The hydrogen, being light, drifted off into space. The oxygen, being heavier, mostly bonded with surface materials and got locked into rocks. The carbon dioxide, which had been dissolved in the oceans and locked up in rocks, was now free in the atmosphere, and the atmosphere just kept thickening. Today, the surface temperature on Venus averages about 462 degrees Celsius. That is about 864 degrees Fahrenheit. Hot enough to melt lead. Hot enough that you do not need to imagine standing on it. You do not get to stand on it. You would be dead in less than a second. The surface pressure on Venus is about 92 times Earth's atmospheric pressure. That is the pressure you would feel at the bottom of about 900 meters of ocean. Not 900. To find a place on Earth with pressure that crushing, you would have to go deeper than any human submarine has ever taken people. The Soviet landers that survived for those few hours did so because they were essentially deep-sea pressure vessels, built with hulls thick enough to handle the weight of an ocean's worth of atmosphere. The sky overhead, if you could somehow see it, is a thick yellow gloom full of clouds made of sulfuric acid. The clouds rain, but the rain never reaches the surface. It evaporates back into the atmosphere on the way down because the lower atmosphere is so hot that liquid sulfuric acid cannot stay liquid in it. So the sky has weather, and the weather has acid, and the acid never lands. This is what Venus is now, a place where lead would puddle on the ground, a place where the air weighs 92 times what our air weighs, and that air is poisonous and corrosive and full of acid rain that never reaches the surface. A place that is by any reasonable definition hell. There is a way I keep coming back to this. Something everyone has done at one point or another. You put a pot of water on the stove. You turn the burner on. You walk away planning to come back when it boils, but you get distracted. You take a phone call. You answer the door. You forget about the pot. When you remember, you walk back into the kitchen and the bottom of the pot is glowing and the water is gone. That is Venus. For a long time, the pot was fine. The water simmered. You could still see the surface of the water. You could still see the bottom of the pot. You could still cook in it. Then, slowly, the water level dropped. Then the pot was dry. Then the pot was glowing. Venus has been a glowing pot for 700 million years, and the burner will not turn off. Here is the part that for me makes Venus the harder world to think about than Mars. The oceans do not completely vanish without leaving a trace. If you look at the chemical composition of Venus's atmosphere with a sensitive enough instrument, and you measure the ratio of two kinds of hydrogen in the upper atmosphere, you find something that does not make sense unless Venus used to have a lot more water than it does now. There is regular hydrogen, the kind with one proton in the nucleus, and there is deuterium, the heavier kind, with a proton and a neutron. Deuterium is rare on Earth. It makes up about 1 part in divorcees 100 of the hydrogen in our oceans. On Venus, the ratio of deuterium to regular hydrogen is roughly 150 times what it is on Earth. That is not a small number. That is the kind of number that has only one good explanation. Light hydrogen escapes into space more easily than heavy hydrogen because light things move faster at any given temperature. And the lightest things in the upper atmosphere are the ones that get knocked off into space by solar wind and ultraviolet light. So, if you start with a planet that has both kinds of hydrogen mixed in its oceans, and you boil those oceans into the upper atmosphere, and you let solar radiation work on that water vapor for a few billion years, the regular hydrogen gets stripped away faster, and the deuterium hangs around. Over time, the ratio of heavy to light hydrogen in the remaining atmosphere goes up. So, when you measure Venus's atmosphere today, and you find 150 times Earth's deuterium ratio, what you are measuring is the chemical fingerprint of an ocean's worth of water that boiled into space billions of years ago, with the lighter component carried off first, leaving the heavier components behind in the air. The water is gone. The trace of the water is not gone. There is a kind of grief that comes with that detail when you sit with it for a minute. We do not usually think of planets as having ghosts, but Venus has one. It is chemical. It is measurable. It is there. The ocean that used to be on Venus is, in a real sense, still hanging in the air, just as a ratio of isotopes, just as a number on a spectrometer, the shape of an absence. We could detect that ratio from Earth with the right telescope 60 light-years away if Venus existed in a system around another star and we had the right instruments pointed at it. We could measure the deuterium signature in its atmosphere, and we could say with high confidence that this planet used to have a lot of water and now does not. We could say it without ever going there. We could say it without ever sending a lander. We could read the obituary from a distance. There may be planets out there right now that we have already done that with. We may not have realized what we were looking at. The hardware to measure this kind of thing reliably across light years is just now coming online with the James Webb Space Telescope and a generation of ground-based extremely large telescopes coming in the late 2020s and 2030s. The first time we read a Venus-like ghost on an exoplanet, we will not be making a discovery. We will be confirming something the universe has been recording on its own, the fingerprint of a former ocean. Venus's porch light is still on. The light has been on for 4 billion years. The house burned down inside, so now we have 2 dead worlds in our own neighborhood. Mars killed by a cooling core and a vanished atmosphere. Venus killed by a runaway greenhouse and an ocean's worth of water boiled into space. Different deaths, same result. 2 planets the same age, the same materials, the same construction, the same starting conditions, one of them in the dust, one of them in the fire, Earth in between, which raises a question that ought to make anyone uncomfortable. How stable is any habitable window anywhere? If 2 of the 3 rocky planets that started inside the Sun's habitable zone have already lost their habitability by completely different mechanisms, what does that tell us about the 3rd one? That is where we have to look next. Because as it turns out, the habitable zone itself is not a place you can plant a flag in and stay forever. It moves. When people first hear about the habitable zone, the image that gets planted in their head is a kind of permanent neighborhood. You imagine a ring around a star, and inside that ring, it is just right, and outside that ring, it is not. The planets inside the ring are the good ones. The planets outside the ring are too hot or too cold. Earth is inside the ring, and that is why we get to exist. And that is basically the end of the story. Almost none of that is right. The habitable zone is real. The math behind it is real. It is very specifically the range of orbital distances from a star at which liquid water could in principle exist on the surface of a planet, given some basic assumptions about atmosphere and reflectivity. For our Sun, look up on a clear summer night, away from city lights, and you might see a faint smudge of the Milky Way stretching across the sky. Somewhere between the constellations Aquila and Sagittarius, there's a tiny patch of darkness called scutum, Latin for shield. It's almost invisible to the naked eye. No bright stars mark it, no ancient myths celebrate it. To most people, it's just empty space. But that emptiness is a lie. Behind that quiet shield, at the far edge of our galaxy's busy inner arm, something impossible is burning. A star so enormous that if you swapped it with our Sun, its outer layers would reach beyond the orbit of Saturn. A star whose volume could swallow 10 billion suns. A star so big that according to the standard equations of stellar physics, it should not be able to exist. This is the story of the largest star we have ever found, a red supergiant named Stephenson 2-18. And it turns out that its size has forced astronomers to question what they thought they knew about the limits of nature. We will walk through the discovery, the controversy, the physics that seems to forbid stars this large, and the unsettling possibility that this monster might already be dead. It all started in the late 1980s with an astronomer named Charles Stephenson. He wasn't chasing records. He was doing a routine survey of the sky in infrared light, looking for cool red stars that are invisible to the human eye. Most of what he found were ordinary red dwarfs and distant giants, nothing that would make headlines. But in 1990, Stephenson aimed his telescope at that patch of sky in scutum. He was using a technique called objective prism spectroscopy, which spreads starlight into rainbows so you can identify the type of star. When he developed the photographic plates, he saw something odd, a tight cluster of deep red signatures, all in one small region. They were the unmistakable fingerprints of red supergiants, dying stars that have puffed up to enormous sizes. He had discovered a cluster he later named Stephenson 2, and inside it, he numbered the brightest star as number 1. That star would eventually become known as Stephenson 2-18, but at the time, nobody paid much attention. Stephenson published his catalog quietly. For 17 years, almost nobody touched it. Then, in 2007, a team led by astronomer Ben Davies took a serious look. They confirmed that the cluster was packed with red supergiants, eventually counting 26 confirmed members. That is the highest concentration of red supergiants known anywhere in the Milky Way. To put it in perspective, our entire galaxy has only about 200 catalogued red supergiants. Finding 26 in one small cluster is like walking into a single classroom and finding 26 lottery winners. It shouldn't happen by chance. Something must have triggered a baby boom of massive stars in that region about 14 to 20 million years ago. And now they are all entering their final, swollen phase at the same time. Among these giants, one star stood out. It was far brighter than the others, so bright that it shouldn't statistically be there. That star, Stephenson 2-18, is the focus of our story. At this point, you might be wondering, just how big is it? The number most often quoted is 2,150 solar radii. In plain English, that means you would have to line up 2,150 of our sun's edge to edge to span the diameter of this star. But numbers alone fail to capture the scale, so let's do a thought experiment. Take our sun, which is already enormous. You could fit about 1 million Earths inside it. Now imagine replacing the sun with Stephenson 2-18. Mercury, Venus, Earth, Mars, gone, vaporized in seconds. The asteroid belt, gone. Jupiter, the giant of our solar system, would be inside the star. Saturn, with its beautiful rings, would be skimming the surface, some calculations placing it just barely inside. Light takes about 2.5 hours to cross this star from one side to the other. That's a photon born in the core that will be older than your morning coffee by the time it reaches the other edge. The volume is even more mind-boggling, roughly 10 billion times the volume of the sun. That's a factor that our brains simply can't hold. But the star's density is the opposite extreme, because all that volume is filled with extremely thin gas. The average density of Stephenson 2-18 is less than the density of the air in your living room. In fact, it's comparable to the upper atmosphere of Earth. The star is mostly empty space, held together by a delicate balance of gravity and pressure. Now here's where physics enters the picture. In 1961, a Japanese astrophysicist named Chushiro Hayashi calculated that there is a hard upper limit to how large a stable star can become. He showed that as a star's surface cools below a certain temperature, around 3,500 Kelvin, the way energy moves through its outer layers changes. The outer envelope becomes fully convective, like a pot of boiling water. And beyond that point, the equations for hydrostatic equilibrium, the balance between gravity pulling in and pressure pushing out, simply have no solution. In other words, a star cannot hold itself together if it gets too big. This boundary is called the Hayashi limit, and for decades it has been considered a firm wall. The theoretical maximum radius for a red supergiant is roughly 1,500 times the Sun. Stephenson 2-18, with its claimed 2,150 solar radii, sits well past that wall. If the measurements are correct, this star is doing something the textbook equations say is impossible. But does it really break physics? Not in the literal sense. No star can violate the laws of thermodynamics. What it does is challenge our models. The Hayashi limit is derived from certain assumptions: spherical symmetry, no magnetic fields, no rotation, no mass loss. Real stars are messier. Stephenson 2-18 might be showing us that under extreme conditions, rapid mass loss, chaotic pulsations, very low surface gravity, the limit can be stretched, at least temporarily. Alternatively, the star might be in a brief unstable phase, swollen to this size just before it either collapses or blows off its outer layers. One way or another, this star is a test of our understanding. And the controversy isn't just philosophical. It hinges on a single frustrating measurement. Almost every wild claim about Stephenson 2-18 traces back to one number: its distance. In astronomy, distance is the foundation. Once you know how far away a star is, you can convert its apparent brightness into true luminosity, its angular size into physical radius, its motion into real velocity. Get the distance wrong, and everything derived from it is wrong by the same factor. For Stephenson 2-18, the distance is a mess. When Charles Stephenson first estimated the distance to the cluster, he calculated about 30 kiloparsecs, nearly 100,000 light-years. That would have placed it on the far side of the Milky Way, almost outside our galaxy. But later studies, using better methods, brought the cluster much closer, around 5.8 kiloparsecs, or about 18,000 to 19,000 light-years. That's still far, but well within the galaxy. The problem is that Stephenson 2-18 itself might not belong to the cluster. Its velocity through space, measured by the Doppler shift of its light, is about 89 kilometers per second. The average of the other cluster stars is about 109 kilometers. That 20 kilometers difference is large enough to suggest that the star could be a foreground or background object, superimposed by chance. If it's in the foreground, it's closer and smaller. If it's in the background, it's even larger. If it belongs to the cluster, the headline 2,150 solar radii stands. For years, astronomers have argued this point. The most careful analysis of the star's motion, combined with the fact that its radial velocity has remained stable, suggests it's not being pulled by a binary companion. Some researchers think the 20 kilometers difference is caused by the star's own outflow. We might be measuring the speed of gas streaming toward us, not the star itself. This explanation is plausible but unproven. The upshot is this: the distance to Stephenson 2-18 has an uncertainty greater than 50%. It could be anywhere from about 9,000 light-years to 30,000 light-years. Move the star within that range, and its radius could shrink to a few hundred solar radii, still big, but not record-breaking, or swell to over 3,000 solar radii. The reigning champion is built on shaky ground. Despite these uncertainties, the star's behavior tells us that whatever its exact size, it is extraordinary. Observatories around the world have monitored its brightness for years, and the light curve is chaotic. Stephenson 2-18 pulsates irregularly, with no clean period. Its surface temperature, around 3,200 Kelvin, is cool enough that molecules like titanium oxide can survive in its atmosphere, another sign that it is pushing the boundaries of stellar stability. The star is also losing mass at a ferocious rate. Infrared observations reveal a vast shell of dust around it, material that was once part of the star's outer envelope. The mass loss rate is among the highest ever measured for a red supergiant, comparable to the extreme star VY Canis Majoris. Every year, this star sheds the equivalent of a small planet. Over the next tens of thousands of years, it will peel itself down to its core. That mass loss is driven by multiple mechanisms. Radiation pressure from the star's enormous luminosity pushes on gas and dust. The low surface gravity makes it easy for material to escape, and the star's own pulsations act like a slow-motion kick, launching gas upward with each cycle. The result is a stellar wind that is not steady but episodic, bursts of high outflow alternating with quieter periods. The surrounding dust shell is not smooth. It has clumps and asymmetries, recording the star's recent history of violent outflows. So what is really happening inside this star? Deep in its core, fusion is still going on, but the fuel is running out. Stephenson 218 likely began its life as a star with a mass between 20 and 40 times that of the Sun. It burned through its hydrogen in a few million years, then helium, then carbon, each stage shorter than the last. Right now, it is probably fusing helium into carbon and oxygen, or it may have already moved on to carbon burning. The exact stage is unknown, but we know it is near the end. A massive star dies when its core turns to iron. Iron cannot fuse to release energy. Instead, fusion stops. The core collapses under its own gravity in less than a second. The collapse triggers a shock wave that tears the star apart, a supernova. For Stephenson 2-18, that moment could come at any time. In cosmic terms, any time could be tomorrow or 100,000 years from now. But because the star is 18,000 light-years away, the light we see today left it during the last ice age. It is entirely possible that the star has already exploded, and the flash of that explosion is racing toward us at the speed of light. One evening, without warning, a new star will appear in the constellation Scutum, so bright it will be visible in daylight. It will outshine every other star in the night sky for weeks, then gradually fade over months. When that happens, every controversy about Stephenson 2-18 will be settled in a single moment. The supernova will tell us its true mass, its true structure, and the nature of its explosion. Neutrino detectors deep underground will pick up the first signal hours before the light arrives. Telescopes around the world and in space will capture the entire event in exquisite detail. It will be one of the most studied astronomical events in human history. And what will be left behind? A neutron star or a black hole, depending on the star's final mass. If the core is below about 2.5 solar masses, it becomes a neutron star, a ball of neutrons about the size of a city, spinning rapidly, maybe a pulsar. If the core is heavier, it collapses all the way to a black hole, an object from which no light can escape. Either way, the star that once challenged our theories will become a compact remnant, while its enriched debris will seed the surrounding space with heavy elements, carbon, oxygen, iron, the ingredients for future planets and life. Let's step back and think about what this star teaches us. The Hayashi limit is not a law of nature in the way that conservation of energy is. It is a mathematical boundary derived from assumptions about stellar structure. Stephenson 2-18, if its size is real, tells us that those assumptions are not absolute. Real stars can temporarily puff up beyond that limit, especially when they are losing mass rapidly and their outer layers are barely held together. The limit becomes fuzzy, not a wall, but a narrow region where stability is rare but not impossible. This is a recurring theme in astronomy. The universe is more inventive than our models. We build theories based on average conditions, and then nature throws a curveball. Stars like this one force us to refine our equations, to include more realistic physics, rotation, magnetic fields, dynamic atmospheres, episodic mass loss. Each outlier reveals a gap in our understanding. There are other giant stars that also flirt with the Hayashi limit. WOH G64 in the Large Magellanic Cloud, VY Canis Majoris, NML Cygni. Stephenson 2-18 is the most extreme candidate, but it is not alone. Collectively, these monsters are teaching us that the upper end of stellar size is not a hard cutoff, but a gradual, messy boundary where stars become increasingly unstable. The title of biggest star ever found is a moving target. Better measurements often demote previous champions. UY Scuti once held the crown with an estimated 1,700 solar radii, until Gaia parallax measurements slashed it to about 755. Stephenson 2-18 might suffer the same fate when more precise data arrives. Or it might keep the crown and force a rewrite of the textbooks. Either way, the star itself doesn't care what we call it. It sits there in the dusty depths of Scutum, burning through its last reserves, shedding its skin, pulsating, waiting for the final collapse. Its light, ancient and red, reaches us across 18,000 years of space, carrying the story of a star that seems to defy the rules. And that story is far from over. Every night that we look up at that faint, empty patch of sky, we are looking at a ticking clock. Somewhere out there, the largest star we know might already be gone. The light of its death could be on its way right now, crossing the interstellar void, carrying the answer to every question we have asked about it. When that light finally arrives, whether next week or 100 millennia from now, it will be a cosmic event that unites the entire world in wonder. It will remind us that the universe still holds surprises, that our understanding is always incomplete, and that the biggest stars, even when they challenge our limits, eventually bow to the same physics that holds every atom together. Stephenson 2-18 is not a break in the laws of nature. It is a revelation of how much more we have to learn. And in the meantime, the star burns on, indifferent to our debates, quietly writing its own final chapter. But the story does not end with that final chapter. The real impact of Stephenson 2-18 stretches far beyond its own fiery death. It is a window into a process that shapes the entire galaxy, one that we are only beginning to understand. Every red supergiant that explodes flings heavy elements into space: carbon, oxygen, silicon, iron. These are the building blocks of planets and of life. The star that seems to defy physics is actually a cosmic factory, manufacturing the raw materials for future worlds. If it has already exploded, its debris is now mixing with interstellar gas, enriching the Scutum Centaurus arm for generations of stars yet to be born. The very atoms that will one day form new rocky planets, maybe even new biospheres, were forged in the core of this singular giant. That is the deeper truth behind the headline. The largest known star is not a freak accident. It is a natural outcome of a young, massive cluster that formed in a starburst event millions of years ago. Its existence tells us that star formation can produce truly extreme objects, even if they are rare. By studying Stephenson 2-18, astronomers learn about the conditions in its birthplace, the density of the original gas cloud, the rate at which stars formed, the initial mass function that governed which stars were born. Every piece of data we extract from this star is a clue to the history of that entire region of the galaxy. There is another lesson, one that applies to every branch of science. Certainty is hard to come by. The star's size, mass, luminosity, age, distance, all of them come with asterisks. The public often expects clean answers, but the reality is that astronomy, like all frontier science, is messy. The uncertainties are not failures. They are honest reflections of the limits of our instruments and models. And that humility is a strength. It means we are always ready to be corrected by new data. Stephenson 2-18 has already been corrected once, from Stephenson's 1990 distance to the modern value, and it will be corrected again. The headline we use today might be outdated tomorrow. That is not a flaw in the science. It is the engine of progress. So where do we go from here? The next few years will be pivotal. The James Webb Space Telescope has already begun observing the most dust-obscured regions of the Milky Way. Its infrared vision cuts through the shrouds that hide stars like Stephenson 2-18. In the coming cycles, astronomers will use Webb to measure the star's spectral energy distribution with far greater precision, to map its dust shell in detail, and perhaps to resolve surface features that are currently blurry. The extremely large telescope, with its 39-meter mirror, will be able to detect the star's photosphere as more than a point of light. It might see the giant convection cells, the asymmetries, the pulsations. For the first time, we will have direct images of the largest known star. And then there is Gaia. The space telescope continues to map the galaxy with ever-increasing accuracy. Future data releases will refine the parallax of Stephenson 2-18, reducing the distance uncertainty from 50% to maybe 10% or less. When that happens, the star's true size will become clear. If it turns out to be 1,500 solar radii, the controversy fades. If it stays at 2,150, the textbooks will need a new chapter. Either outcome is valuable because it forces us to confront the limits of our knowledge. Meanwhile, the star itself does not wait. Every second, it burns through thousands of tons of nuclear fuel. Its core slowly shrinks and heats. The surrounding envelope gets looser. The pulsations may become more violent, the mass loss more extreme. At some point, the core will reach the end of its fusion chain, and then, in a few minutes of cosmic violence, the star will become something else entirely. Imagine that moment. Deep inside, a sphere of iron about the size of Earth, weighing maybe 2 solar masses, suddenly passes the threshold. The iron core can no longer support itself. The pressure becomes so intense that electrons are forced into protons, turning them into neutrons. The core collapses from thousands of kilometers in diameter to just a few dozen kilometers in less than a second. The infalling outer layers slam into this rigid neutron core and bounce. A shock wave forms, blasting outward. In the next few hours, it tears through the rest of the star. The energy released is so colossal that for a brief time, the explosion outshines the combined light of every other star in the Milky Way. A single point in scutum becomes the brightest object in the night sky, visible even in daylight. That is the future of Stephenson 2-18. And because the star is 18,000 light-years away, the light from that explosion is probably already on its way. The neutrino burst from the core collapse will arrive hours ahead of the visible flash. Underground detectors around the world, Super Kamiokande in Japan, Ice Cube at the South Pole, will record a brief spike in events. Astronomers will get a warning. Then the sky will change. For the public, this will be an unforgettable event. People will step outside and see a new star, brighter than Venus, casting shadows. It will be visible in cities, through clouds, even during twilight. For weeks, it will dominate conversation. Social media will light up. News channels will anchor entire segments around it. Scientists will scramble to point every available telescope at it. The data flood will be unprecedented. We will measure the explosion's chemistry, its geometry, its light curve, with exquisite detail. We will finally know the true mass of the progenitor. We will see whether it formed a neutron star or a black hole. We will watch the remnant fade into a supernova remnant that will glow in radio and X-rays for thousands of years. And after the excitement fades, the legacy remains. The heavy elements ejected by that supernova will drift through the Scutum Centaurus arm. 1,000,000 years from now, some of that carbon and oxygen will be incorporated into a new generation of stars and planets. In 1,000,000,000 years, an alien astronomer in that region might look up at a sky enriched by the death of Stephenson 218. They will never know the name we gave it, but they will be made of its atoms. That is the ultimate meaning of this star. It is not just a record holder or a source of controversy. It is a link in the chain of cosmic evolution. It reminds us that the universe is a place of constant change, that even the largest, most stable-seeming objects are temporary, and that our own existence depends on the violence that ends such stars. So, the next time you look up at the constellation Scutum, that faint, almost invisible shield in the summer sky, remember what hides behind its quiet patch of darkness. A star that could swallow our entire solar system out to Saturn. A star that challenges the equations we thought were settled. A star that is bleeding its outer layers into space, preparing for a spectacular death. A star that might already be dead, its final flash racing toward us at the speed of light. And remember that the story of Stephenson 2-18 is not a closed chapter. It is an open investigation, a testament to how much we still don't know about the vast, intricate cosmos we call home. The biggest star ever found might not be the biggest star there is. There could be others, even more extreme, hidden in the dust of more distant spiral arms. The galaxy is full of secrets. Every time we push our instruments further, we find something that makes us rethink everything. That is the beauty of science. It never settles. It never stops asking. And as long as stars like Stephenson 218 burn, they will keep challenging us to look deeper, measure more carefully, and imagine more boldly. The biggest star ever found is bigger than physics allows, or so it seems. But physics, like the star itself, is always evolving. And the truth, when we finally get it, will be more wonderful than any headline. And perhaps that is the greatest lesson of all. The universe does not hand us tidy answers. It hands us puzzles wrapped in dust and distance. Stephenson 2-18 is not a failure of physics. It is an invitation to refine it, to stretch our understanding a little further. Every measurement, every debate, every new observation adds another thread to the tapestry. The star burns on, waiting, and so do we, patiently, with telescopes aimed at the shield, ready for the next revelation. There is a very real chance that the most powerful machine ever built by human hands could, at any moment, produce something that has haunted our nightmares for decades, a black hole. Not some distant, astronomical monster lurking in the heart of a galaxy, but a microscopic singularity, born right here on Earth, inside a concrete tunnel under the Swiss-French border. And if you think that sounds like the plot of a sci-fi thriller, you are not alone. When the Large Hadron Collider first powered up in 2008, headlines screamed that the end of the world was imminent. Lawsuits were filed to stop the experiment. People genuinely believed that a man-made black hole would consume the planet before they could finish their morning coffee. Of course, we are all still here. The world didn't end. But here's the twist. CERN's own documentation, even today, admits that the LHC could create a black hole. The question is not whether it's possible. The question is what would happen if it did? And the answer, as we'll see, is far stranger and far more fascinating than you might expect. Let's start with the machine itself. The Large Hadron Collider is a marvel of engineering. A 27-kilometer ring of superconducting magnets, chilled to temperatures colder than outer space, buried 100 meters underground. Inside that ring, two beams of protons are accelerated to 99.9991% the speed of light. That is so close to light speed that the protons are moving about 3 meters per second slower than the ultimate cosmic speed limit. When these beams cross, which happens 1 billion times every second, the protons slam into each other with a combined energy of 13.6 tera-electron volts. That energy is the key. According to Einstein's famous equation, energy can be converted into mass. In the extreme conditions of those collisions, heavy particles that haven't existed since the first moments after the Big Bang can be created, if only for a fleeting instant. This is how we discovered the Higgs boson. This is how we study the fundamental building blocks of matter. But energy can also, in theory, be concentrated into a tiny region of space with enough force to warp space-time into a black hole. So why would anyone worry? Because black holes, in the popular imagination, are cosmic vacuum cleaners. You get too close and you're gone, stretched, spaghettified, and erased from existence. The idea of one popping into existence in a laboratory seems like a catastrophic mistake. But the physics behind it is nuanced. To understand what would actually happen, we need to talk about the energy required to make a black hole in the first place. In our everyday universe, black holes form when massive stars collapse. You need a star at least 20 times the mass of our Sun to crush its own core into a singularity. That's an astronomical amount of matter. The LHC, on the other hand, is smashing together particles that weigh essentially nothing. How could that possibly create a black hole? The answer lies in a concept called the Planck energy. The Planck energy is a theoretical threshold, a value so enormous that classical physics breaks down, and quantum gravity must be considered. To give you a sense of scale, the Planck energy is about a quintillion times larger than the energy the LHC can produce. By that measure, there is no chance whatsoever that the LHC could ever create a black hole, not even close. However, and this is a big however, that calculation assumes our universe has only the 4 dimensions we are familiar with, 3 of space and 1 of time. But many theoretical physicists, especially string theorists, propose that additional spatial dimensions exist, curled up so tiny that we can't perceive them. If those extra dimensions are real, they change the rules of gravity. Instead of gravity being incredibly weak, it could become much stronger at very small scales. That would lower the Planck energy, potentially down to a level that the LHC can reach. In that scenario, a collision at 13.6 tera-electron volts might just be enough to create a microscopic black hole. Now, this is still speculative. No one has proven the existence of extra dimensions. But if they do exist, then yes, CERN could theoretically produce a black hole. And that brings us to the crucial question: what would happen next? Most people assume instant doom. The black hole would start devouring matter, growing larger, and then sink to the center of the Earth, consuming the planet from the inside out. It's a terrifying image, and it has fueled countless doomsday scenarios. But the reality is almost comically anticlimactic. In all likelihood, the black hole would evaporate practically the moment it formed. This is because of a phenomenon predicted by Stephen Hawking in 1974, known as Hawking radiation. Hawking showed that black holes are not truly black. They emit a faint glow of radiation due to quantum effects near the event horizon. This radiation carries away energy, causing the black hole to lose mass. For a large black hole, like one at the center of a galaxy, this process takes unimaginably long, trillions of years. But for a tiny black hole, the evaporation is incredibly fast. A black hole with the mass of a few protons would radiate away its energy in a fraction of a second, releasing about the same energy as a grain of sand dropping a few centimeters. If you were standing nearby, you might not even notice. The detectors at CERN are sensitive enough to spot the telltale signature of such an event, but so far, they haven't seen anything. That doesn't mean it's impossible. It could just mean that extra dimensions don't exist at the energies we've probed. But even if Hawking radiation is wrong, and the black hole somehow stabilizes, the danger remains surprisingly low. Let's imagine a worst-case scenario. No Hawking radiation, extra dimensions exist, and a microscopic black hole is born. What would it do? First, it would have a tiny mass, maybe a few trillionths of a gram. That's not enough to exert any significant gravitational pull. Gravity is the weakest of the fundamental forces. A paperclip on your desk exerts more gravitational force on you than that black hole would. But wouldn't it start gobbling up nearby matter? The key is scale. A microscopic black hole's event horizon is smaller than a proton. For it to absorb anything, that particle must wander directly into that infinitesimally small region. Atoms, however, are mostly empty space. The nucleus of an atom is like a marble sitting in the middle of a sports stadium. The electrons are like tiny gnats buzzing around the stands. For our black hole to hit a nucleus, it would have to thread a needle of astronomical precision. Even if it did, the black hole would absorb that nucleus, gaining a minuscule amount of mass. But then what? Without an electric charge, the black hole would simply fall through the surrounding matter. It wouldn't be attracted to atoms because gravity is so weak, and it wouldn't be repelled by electromagnetic forces because it's neutral. So it would sink through the floor, through the rock, straight toward the center of the Earth. But it would keep going. In fact, it would pass right through the core and out the other side, oscillating back and forth like a pendulum, losing energy only through extremely rare collisions. Each collision would add a tiny bit of mass, but the probability of a collision is so low that even over billions of years, the black hole would remain microscopic. By the time the Sun becomes a red giant in 5 billion years, the black hole would still be tiny and harmless, quietly oscillating through the planet. This is where we address the idea you may have heard, that a black hole would sit harmlessly at Earth's center. Actually, that's not quite accurate for a neutral black hole. It wouldn't stop at the center. It would pass through it, like a ghost. But because of Earth's gravity, it would gradually slow down due to tidal forces and rare interactions with matter. Over a very long time, it could eventually become trapped at the center, oscillating with decreasing amplitude. But even then, it would pose no danger. Its gravitational pull would be negligible. The only way it could grow is if it somehow encountered dense matter. But the core of the Earth is already dense, but not dense enough to meaningfully increase the black hole's capture rate. You would need an object with nuclear densities, like a neutron star, for a black hole to accumulate mass quickly. Our planet is far too diffuse. So yes, a microscopic black hole could end up sitting at Earth's center. But it would be as harmless as a dust mote in a cathedral. It would not consume the planet. It would not collapse the Earth into a sphere of nothing. It would just sit there, and you would never know. This might seem anticlimactic. After all, we are talking about the possibility of creating a black hole, the most extreme object in the universe. And it turns out it would be about as dangerous as a spilled cup of coffee. But that's physics for you. The universe has a way of being far more mundane than our fears imagine. However, there is a different kind of catastrophe that is genuinely terrifying, and it's one that CERN could theoretically trigger. It's not a black hole. It's something called vacuum decay. Vacuum decay is the idea that our universe might be in a false vacuum state, a state that is stable for now, but not the lowest possible energy state. Think of it like a ball sitting in a small dip on a hillside. It's stable, but if you give it a big enough push, it could roll down into a deeper valley, releasing a massive amount of energy. That deeper valley is the true vacuum. If a region of space were to tunnel into that true vacuum, it would expand outward at the speed of light, rewriting the laws of physics as it went. Everything in its path, atoms, molecules, stars, galaxies, would be torn apart and replaced by a different set of fundamental particles. The universe as we know it would cease to exist. And here's the terrifying part. Very high-energy particle collisions, like the ones at the LHC, could theoretically catalyze that transition. The energy of the collision might be enough to nudge a tiny patch of space-time into the true vacuum, creating a bubble that expands without bound. This is not a fringe idea. It's a genuine, if extremely unlikely, possibility discussed in serious physics literature. Unlike a black hole, which would likely be harmless, vacuum decay would be instantly and utterly fatal to the entire universe. It's arguably the most catastrophic event that could ever happen. So, why aren't we more worried about vacuum decay? Because the energy required to trigger it is far, far beyond anything we can produce. The LHC operates at 13.6 TeV. The energy needed to nucleate vacuum decay is thought to be at the Planck scale, quintillions of times higher. But there is a catch. Some theories suggest that the Higgs boson itself, which the LHC discovered, could be a sign that our vacuum is metastable. In fact, measurements of the Higgs mass hint that the universe might be in a false vacuum, teetering on the edge of decay. If that's true, then a high-energy collision might, in principle, provide the necessary push. But the numbers still suggest we are safe by many orders of magnitude. Still, the fact that vacuum decay is even a mathematical possibility makes the black hole fear seem almost quaint. A black hole would be a local event. Vacuum decay would be the end of everything. And it's something that CERN, however unintentionally, is at least theoretically tinkering with. Now, you might recognize some of these ideas from popular culture. The anime and visual novel series Steins Gate famously revolves around a group of amateur scientists who accidentally create a microwave that can send messages to the past. The story's central tension comes from the fear of altering history, but the show also references real particle physics, including the Large Hadron Collider and the possibility of black hole creation. In one memorable scene, the protagonist, Okabe Rintaro, obsesses over the idea that the LHC could generate a black hole that would destroy the world. The show uses that fear as a metaphor for the unintended consequences of meddling with forces we don't fully understand. It's a brilliant narrative device because it taps into the very real anxiety that many people feel when they hear about experiments like CERN's. We worry that scientists are playing with fire and that one misstep could lead to catastrophe. While Stein's full gate is fiction, the underlying science it plays with is real. The LHC does push the boundaries of what we know, and while the specific black hole scenario in the show is dramatized, it captures the spirit of the public's imagination and our collective fascination with apocalypse. So, where does that leave us? CERN has been running the LHC at increasingly higher energies for over a decade. It has performed quadrillions of collisions. No black holes have been observed. No vacuum decay bubbles have been detected. The safety analyses that were conducted before the LHC turned on concluded that the risk is essentially zero. Those analyses considered both natural and artificial scenarios. They pointed out that cosmic rays, high-energy particles from space, bombard Earth's atmosphere with energies far exceeding the LHC's. If the LHC could create a dangerous black hole, cosmic rays would have already done so billions of times over. The Earth is still here. That is the strongest piece of evidence that the LHC is safe. But it's worth noting that cosmic rays hit stationary particles in the atmosphere, while the LHC smashes particles moving in opposite directions. That difference matters for some exotic hypotheses, but for the black hole scenario, it's not significant. The energy per collision is what counts, and cosmic ray collisions can reach much higher energies than the LHC. So if nature hasn't managed to produce a planet-eating black hole in 4.5 billion years, it's extremely unlikely that we will. However, the fear persists. It's baked into our psychology. We are naturally cautious about technology that we don't fully understand. The LHC represents a level of sophistication that few of us can grasp. It's easy to imagine the worst, but the scientists at CERN are not reckless. They are among the most careful, peer-reviewed, safety-conscious researchers on the planet. They have run exhaustive risk assessments, they have published their findings, and they continue to operate the LHC because the benefits of understanding the universe far outweigh the minuscule theoretical risks. One of the most important lessons from this whole story is that our intuition about black holes is often wrong. We think of them as voracious eaters, but in reality they are just gravity wells. Gravity is weak. A black hole with the mass of a mountain would have an event horizon smaller than a proton. It would have the gravitational pull of a mountain, yes, but that's not enough to suck in the Earth from a distance. You'd have to be very, very close. The idea that a microscopic black hole could somehow grow unstoppably is based on a misunderstanding of how matter falls into black holes. Matter has to lose angular momentum and energy to spiral inward. In a diffuse environment like the Earth's interior, a tiny black hole would hardly ever interact with anything. It's like trying to catch a single specific grain of sand in a hurricane while blindfolded. The odds are astronomically against it. And what about that black hole with no charge? We mentioned it would fall through matter, but if it had an electric charge, it would be repelled by the electromagnetic fields of atoms and would likely get stuck in the floor very quickly. A charged black hole would not sink to the center. It would be pushed and pulled by electromagnetic forces, and it would likely come to rest somewhere in the rock. Still harmless? So even in the most exotic scenarios, we are safe. Now, let's circle back to vacuum decay. Some might argue that we should be more afraid of that than black holes, and in a sense, they're right. Vacuum decay is the ultimate existential threat, but it's also so incredibly unlikely that worrying about it is like worrying about a meteor hitting your house while you're in the basement. The LHC simply doesn't have the energy to trigger it, and even if it did, the conditions required are so specific that the probability is effectively zero. The universe has been around for 13.8 billion years, and as far as we know, no vacuum decay has ever happened. That doesn't mean it can't, but it does mean that if it were easy, it would have already occurred. There is another fascinating angle to all of this: the idea that the LHC could create a black hole that would not evaporate and would not grow, but instead would behave like an exotic particle. This is where we can tie in the cultural reference that many of you might have encountered. In Stein's Gate, the characters fear that the LHC will create a black hole, but they also use the concept of the world line and the idea that the future can be changed. While the show takes creative liberties, it does highlight how our deepest scientific endeavors can inspire stories that explore the human condition. The LHC is not just a machine. It's a symbol of our desire to push boundaries, to understand the very fabric of reality. And sometimes that journey comes with a frisson of danger, just enough to make it thrilling. But the truth is, we are not in danger. Not from black holes, not from vacuum decay, not from portals to hell. The LHC is one of the safest scientific instruments ever built. Every time it turns on, the world does not end. And every time it produces a new discovery, we learn something profound about the universe we live in. That is worth the tiny theoretical risk, if you can even call it a risk. In fact, if the LHC ever did create a microscopic black hole, it would be one of the most exciting discoveries in the history of physics. It would confirm the existence of extra dimensions. It would open a new window into quantum gravity. It would validate decades of theoretical work. And then, that black hole would either evaporate instantly or sit there, harmless, and scientists would study it. They would measure its properties. They would learn how gravity behaves at the smallest scales. It would be a triumph, not a tragedy. So the next time you hear someone say that CERN could create a black hole that destroys the world, you can smile and nod and tell them that even if it did, it would be about as dangerous as a falling leaf. The real danger, if any, lies not in the black hole, but in the human imagination, which can conjure up terrifying scenarios that have no basis in physical reality. But that's part of what makes us human. We imagine the worst, we plan for it, and then we go ahead and explore anyway. That's what science is all about. And if you are still worried, just remember, the universe has been throwing particles at itself for billions of years with far more energy than we can muster. If black holes were easy to make, we would already be living inside one. But we're not. We're here, on a beautiful planet, under a star that has another 5 billion years of life left. And in that time, we have the chance to learn, to grow, and to push the boundaries of knowledge as far as they will go. The Large Hadron Collider is our torch in the dark. It illuminates the unknown, and so far, it hasn't burned us. Now, if you'll excuse me, I need to go check if there's a tiny black hole oscillating through my living room. Probably not. But if there is, I'm not too worried. It's just a ghost of a proton, quietly dancing through the atomic emptiness. And I, for one, think that's beautiful. Thank you for watching. But before we close the book on this topic, there is one more cultural touchpoint that perfectly captures the blend of fascination and fear that CERN inspires. If you are an anime fan, you have almost certainly encountered Steins. Gate, a series that revolves around a group of eccentric friends who accidentally invent a microwave that can send text messages back in time. The protagonist, Okabe Rintaro, is a self-proclaimed mad scientist who constantly obsesses over the idea that the Large Hadron Collider might spawn a black hole and end the world. In one memorable scene, he stares at a news report about CERN, referred to in the show as CERN, and rants about the impending apocalypse. The show uses this anxiety as the central plot device, and it resonates because the fear feels real. We watch Okabe's paranoia, and we recognize a little of ourselves in his dread. But what makes Steins' Gate brilliant is that it also explores the consequences of meddling with time, not just black holes. The LHC becomes a symbol of unchecked scientific ambition, a gateway to forces we cannot control. In the show, CERN is a shadowy organization that uses particle physics to achieve world domination. It's a dramatization, of course, but it reflects the very human worry that our best tools might become our worst enemies. And yet, the reality is far less sinister. CERN is not a secret cabal. It is an international collaboration of thousands of scientists, all working openly and publishing their results. The LHC is not a doomsday device. It is a microscope, the most powerful one we have ever built. It allows us to see the smallest building blocks of nature, and the discoveries it has made, from the Higgs boson to hints of new physics, have reshaped our understanding of the universe. So, why do we keep coming back to the black hole fear? Why does it persist despite overwhelming evidence to the contrary? Part of it is the sheer drama. A black hole is a cosmic horror. It is the ultimate expression of gravity, a place where everything ends. The idea that we could create one in a laboratory feels like we are playing with forbidden knowledge. It taps into a deep-seated narrative archetype, the scientist who unleashes something they cannot control. From Frankenstein to Oppenheimer, this story is woven into our cultural DNA. CERN is just the latest chapter, but there is another reason the fear lingers. The science is genuinely difficult. Even experts disagree on the details of quantum gravity and extra dimensions. So when CERN itself says there is a non-zero chance of creating a black hole, the public hears, "We might all die." They do not always hear the caveats. They do not hear that the chance is astronomically small, or that even if it happened, it would be harmless. They just hear the word black hole, and their imagination runs wild. I can hardly blame them. I have spent years studying this stuff, and I still feel a twinge of excitement when I think about the LHC. It is a machine that smashes protons at nearly the speed of light. It is science fiction made real. Now, let's bring in that other great fear, vacuum decay. I touched on it earlier, but it deserves a deeper look because it is genuinely one of the most awe-inspiring and terrifying concepts in modern physics. Imagine a universe where the laws of physics are not fixed. They are like a landscape of hills and valleys. We live in a valley that seems stable, but it might not be the lowest one. If we could tunnel into the lowest valley, the true vacuum, everything changes. The particles we are made of would no longer be possible. Protons would dissolve, atoms would break apart. The very structure of matter would be rewritten, and the bubble of true vacuum would expand at the speed of light. You would not see it coming. There would be no warning. One moment, you are reading this. The next, the universe as you know it is gone. It is not a violent explosion. It is a silent, instantaneous reconfiguration. Every star, every planet, every living thing would be erased and replaced by something else. Something we cannot even imagine because our physics does not apply there. Before you panic, let me repeat the math. The energy required to trigger vacuum decay is thought to be around the Planck scale, about 10^16 TeV. The LHC operates at 13.6 TeV. That is a gap of 15 orders of magnitude. It is like comparing the energy of a firefly to that of a supernova. But there is a wrinkle. The Higgs boson's mass suggests that our vacuum might be metastable. In simple terms, it means we are living on a knife edge. The universe could, in principle, decay at any moment. But the probability is so low that you are more likely to win the lottery every single week for 1 trillion years. Still, the fact that it is even a possibility makes the black hole fear look almost childish. A black hole is a local event. Vacuum decay is the end of the whole show. So why isn't vacuum decay the headline every time CERN turns on? Because it is harder to dramatize. A black hole is a tangible monster. Vacuum decay is an abstract mathematical ghost. It does not have a maw or an event horizon. It is just a change in the fundamental constants. And yet, if there is one thing that should keep physicists up at night, it is the idea that we might inadvertently nudge the universe into a new state. The good news is that every single cosmic ray collision that has ever happened, and there have been quadrillions, would have had far more energy than anything the LHC can produce. If vacuum decay were that easy, it would have already happened. The universe would not be here. So, we can breathe easy. But it does make for an excellent thought experiment, and it puts the black hole fear into perspective. Now, I want to circle back to a point I made earlier about a charged black hole. Let's paint a picture. Suppose CERN creates a black hole with a net electric charge. That is actually very likely, because the protons being collided have a positive charge, and the resulting black hole would inherit that charge. What happens then? It would not fall through the floor like a ghost. Electromagnetic forces are about 10 to 36 times stronger than gravity at that scale. The black hole would be repelled by the positive charges of atomic nuclei in the ground. It would come to a screeching halt almost immediately. It would essentially be stuck in the concrete, or maybe it would hover just above the floor, unable to penetrate the atomic lattice. And there it would sit, a tiny, charged speck of space-time curvature doing absolutely nothing. It would be like a microscopic dust particle that happens to have an event horizon. You could walk right past it and never know. If you tried to pick it up with a pair of tweezers, you would fail because it is smaller than an atom. The only way to detect it would be to build incredibly sensitive instruments that could sense its gravitational or electromagnetic signature. But even then, It would not pose a threat. It would be a scientific marvel. It would be proof that extra dimensions exist. And then the Nobel Prizes would start rolling in. But here is the kicker. We have not seen any such black holes, not one. The LHC has been running for over a decade. It has produced quadrillions of collisions. If black holes were being created, they would have left a signature. The detectors would have seen a sudden loss of energy and momentum, a particle that disappears into a micro black hole and then evaporates. No such events have been observed. That does not completely rule out the possibility, because if the black holes are very small, their Hawking radiation might be too faint to detect. But it does suggest that if they are being made, they are incredibly rare. And given that cosmic rays have been hitting Earth with higher energies for billions of years, the fact that we are still here is the strongest evidence that microscopic black holes are either not formed or are completely harmless. So, where does that leave us? We have explored the science, the fears, the cultural references. We have looked at black holes, vacuum decay, and the oddities of quantum gravity. We have seen that the LHC is not a doomsday machine. It is a triumph of human ingenuity. It is a testament to our ability to ask big questions and build big machines to answer them. And yes, it carries a tiny theoretical risk. But that risk is so small that it is practically indistinguishable from zero. Every day, you take far greater risks. You drive a car, you eat food, you walk downstairs. All of these activities have a non-zero chance of killing you. The LHC has a non-zero chance of creating a black hole that does absolutely nothing. I know which one I am less worried about. And yet, the fear will not go away. It is part of being human. We are wired to imagine worst-case scenarios. It is a survival instinct. But we also have the ability to reason, to examine the evidence, and to understand the odds. When we do that, we find that CERN is safe, the universe is safe, and the pursuit of knowledge is worth the tiny theoretical gamble. In the end, the story of CERN and black holes is a story about perspective. It is about how our imagination can outrun reality. It is about the line between science fiction and science fact. And it is about the bravery of scientists who dare to push boundaries even when the public is afraid. They do not do it because they are reckless. They do it because they understand the risks, and they know that the rewards, a deeper understanding of the cosmos, are immeasurable. So, if you ever hear someone say that CERN could destroy the world, you can smile and offer them a different perspective. You can tell them that yes, the LHC could create a black hole, but that black hole would be the most harmless thing you have ever seen. It would be a scientific wonder, not a world ender. And if you want to be truly terrified, look up vacuum decay. But even then, take a deep breath. The odds are on our side. Now, I am going to leave you with one final thought. Imagine for a moment that the LHC did create a microscopic black hole. Imagine it survived with no charge and somehow avoided all interactions as it passed through the Earth. Imagine it settled at the center of our planet, a tiny point of infinite density. What would happen? Nothing. It would just sit there. It would take billions of years to eat even a gram of matter. Long before it became a threat, the sun would expand and swallow the Earth. And long before that, humanity would have evolved, or gone extinct, or traveled to the stars. The black hole would be a silent witness to our story, a ghost in the machine of the Earth. And one day, when the planet is gone, it would still be there, drifting through space, a tiny relic of a civilization that dared to reach for the stars. That, to me, is not terrifying. It is beautiful. It is a reminder that even the most extreme objects in the universe are subject to the laws of physics. They are not monsters. They are not gods. They are just consequences of the equations that govern our reality. And we, armed with those equations, can understand them, predict them, and even create them in a controlled environment. That is the power of science. So, thank you for joining me on this journey. I hope you now have a clearer picture of what the LHC can and cannot do. I hope you are less afraid and more curious. And I hope you will continue to ask the big questions, because that is what makes us human. We ask, we explore, we learn, and sometimes we even create little black holes, but we never let them win. Until next time, stay curious. And if you feel a tiny tremor beneath your feet, do not panic. It is probably just a proton, dreaming of becoming a singularity. We like to think we know our place in the universe. We've mapped the stars, calculated the age of everything, and built models that explain galaxies and black holes with staggering precision. But every now and then, the universe reminds us just how little we actually understand. And one of those reminders is a quiet, unsettling realization. We might be living in a bubble. Not a metaphorical bubble of ignorance, but an actual physical void in the fabric of space itself. A region so vast and so empty that it challenges some of the most fundamental assumptions in cosmology. This is the story of the KBC void, a cosmic desert 2 billion light-years across, and why its existence could rewrite everything we thought we knew about the universe, about the expansion of space, and even about the search for extraterrestrial life. Let's start with the scale of things. You've probably heard the numbers before. Our Milky Way galaxy contains somewhere between 100 and 400 billion stars. That's a number so large it's almost meaningless. To try to grasp it, imagine if every one of those stars had at least one planet. That would mean hundreds of billions of worlds just in our own galactic neighborhood. Now multiply that by the estimated 2 trillion galaxies in the observable universe. The total number of planets out there is almost incomprehensible. Some estimates suggest there are more stars in the universe than grains of sand on every beach on Earth. And if even a tiny fraction of those planets are in the habitable zone of their stars, the number of worlds that could support life becomes enormous. So, where is everybody? This is the Fermi Paradox in a nutshell. The universe should be teeming with life, or at least with technological civilizations sending signals across the cosmos. But we have heard nothing. No definitive alien broadcasts, no laser pulses, no Dyson spheres. The sky is silent. For decades, scientists have proposed countless explanations. Intelligent life destroys itself. Civilizations are too far apart. Or maybe we are alone after all. But there is another possibility, one that has gained traction only in the last decade. What if the reason we haven't found anyone is not because they don't exist, but because we happen to live in the cosmic equivalent of a remote village far off the galactic highway? What if we are inside a void so large and so sparsely populated that other civilizations are simply too far away to notice us, and we are too far from them to hear anything at all? That idea might sound like science fiction, but it is grounded in real astronomical observations. In 2013, a team of researchers, led by Ryan Keenan, Amy Barger, and Lennox Cowie, published a paper with a startling conclusion. By analyzing the distribution of galaxies in the nearby universe, they found evidence that our Milky Way is located near the center of an enormous underdense region, a void. And not just any void. This one, now known as the KBC void, named after Keenan, Barger, and Cowie, is about 7 times larger than typical cosmic voids. It stretches approximately 2 billion light-years from end to end. That is so big that if you were to travel at the speed of light from one side to the other, it would take 2 billion years. To put it in perspective, the entire observable universe is about 93 billion light-years across. This void occupies a significant fraction of our local cosmic neighborhood. Before we dive deeper, let's clarify exactly what we mean by a void. In astronomy, voids are regions of space where the density of matter is much lower than average. The universe, on large scales, is not a uniform soup of galaxies. Instead, it has a structure that looks something like a cosmic foam. There are dense clusters of galaxies connected by filaments, and in between those filaments are vast, empty spaces called voids. A typical void might be a few 100 million light-years across and contain only a handful of galaxies, or sometimes none at all. The KBC void, however, is not typical. It is a supervoid, a region where the galaxy count is about 20% lower than the cosmic average. That might not sound dramatic, but it is statistically significant. Within this void, there are far fewer galaxies and therefore far fewer stars than in the regions outside. And because we are near its center, our view of the cosmos is filtered through this local emptiness. Now, you might have heard conflicting information about the Milky Way's location. Some sources say we are in a void. Others say we are in a local group of galaxies that is part of a larger supercluster. So, which is it? Let's untangle this. The Milky Way is part of the local group, which includes Andromeda and about 80 other small galaxies. The local group is, in turn, part of the Virgo supercluster, a much larger structure containing thousands of galaxies. But even the Virgo supercluster is embedded within an even larger structure called the Laniakea supercluster. So we are certainly not in an empty void in the sense that there are no galaxies around us. In fact, our local environment is quite dense compared to the deep voids far away. However, when scientists look at the distribution of galaxies on scales of hundreds of millions to billions of light-years, they find that our region is underdense compared to the average density of the universe as a whole. It's like living in a small town in the middle of a vast desert. The town itself is not empty, but the region around it is far less populated than the fertile plains elsewhere. So, the KBC void does not mean we are alone in our immediate neighborhood. It means that on very large scales, we are situated in a region that is sparser than the cosmic norm. This discovery was met with considerable skepticism at first. The standard model of cosmology, known as LCDM, lambda cold dark matter, is built on a cornerstone called the cosmological principle. This principle states that the universe is homogeneous and isotropic on large scales, meaning that matter is distributed evenly and looks the same in every direction. The existence of a void as large and as deep as the KBC void seems to violate that principle. If the universe is truly homogeneous, how can there be a region 2 billion light-years across with a significantly lower density? Cosmological simulations based on LCDM, such as the Millennium simulation or the MXXL simulation, suggest that structures like the KBC void should be extremely rare. In fact, the probability of such a void forming within the standard model is less than 1%. That immediately raises red flags. Either our observations are wrong, or our model is missing something. But as more data poured in from galaxy redshift surveys that measure the distances and motions of thousands of galaxies, the evidence for the void became harder to dismiss. The KBC void is not just a statistical fluke. It is supported by multiple independent studies. In 2017, a team including Ryan Keenan published an updated analysis confirming the underdensity out to a distance of about 300 megaparsecs, or roughly 1 billion light-years. They found that the matter density in that volume is about 20% lower than the cosmic average. And crucially, this underdensity is not uniform in all directions. It has a structure that influences the apparent motion of galaxies, a phenomenon known as the bulk flow. Galaxies inside the void are being pulled toward the denser regions outside, creating a velocity field that we can measure. This brings us to one of the most exciting implications of the KBC void. It may offer a solution to the Hubble tension. The Hubble tension is arguably the biggest crisis in modern cosmology. To understand it, we need to talk about the expansion of the universe. The universe has been expanding since the Big Bang, and the rate of that expansion is given by a number called the Hubble constant. Think of it as a cosmic speed limit. For every megaparsec, about 3.26 million light-years, farther away a galaxy is, it moves away from us faster by about 70 kilometers per second. But here's the problem. There are two different ways to measure HO, and they give different answers. The first method uses observations of the early universe. By studying the cosmic microwave background, the afterglow of the Big Bang, scientists can infer the conditions of the universe about 380,000 years after its birth. Using the standard LCDM model, they can then extrapolate forward to predict what the expansion rate should be today. This method gives a value of about 67.4 kilometers per second per megaparsec. The second method uses direct observations of nearby galaxies. Astronomers measure distances using standard candles like Cepheid variable stars and Type Ia supernovae, and then measure how fast those galaxies are receding from us. This method gives a value of about 73.0 kilometers per second per megaparsec. The difference is about 8%, and it is statistically significant. It cannot be explained by measurement errors alone. This discrepancy is the Hubble tension. It suggests that either our model of the early universe is wrong, or our understanding of the local universe is incomplete. And that's where the KBC void comes in. If we are living inside a large underdense region, then the expansion rate we measure locally might not be the true cosmic expansion rate. Here's why. Inside a void, there is less matter, so the gravitational pull is weaker. But the surrounding denser regions exert a stronger gravitational attraction, pulling matter outward. This creates an extra apparent motion, making it look like galaxies are moving away from us faster than they actually are. In other words, the void fools us into thinking the expansion is faster in our neighborhood. When scientists model the gravitational effect of the KBC void, they find that the local expansion rate measured from nearby galaxies could be inflated by about 10% compared to the true global expansion rate. that is almost exactly the size of the Hubble tension. So the Hubble tension might not be a sign of new physics like modified gravity or exotic dark energy. It could be a simple geographic effect. We happen to live in a place that skews our measurements. This is a Occam's razor solution that many cosmologists find appealing because it doesn't require us to throw out the entire LCDM model. However, this explanation is not without its own problems. For the void to have such a strong effect, it must be quite deep and quite large. And as we already mentioned, standard LCDM simulations struggle to produce voids of this size and depth. So, the void explanation for the Hubble tension actually compounds the original problem. We now have to explain why such a void exists in the first place. This has led some researchers to consider alternative theories of gravity. One of the most prominent is modified Newtonian dynamics, or MOND. MOND was originally proposed to explain the rotation curves of galaxies without invoking dark matter. It suggests that at very low accelerations, like those found at the edges of galaxies, gravity behaves differently than Newton predicted. When applied to cosmological scales, MOND predicts that structure formation happens faster than in LCDM. In a MOND universe, large voids like the KBC void are much more likely to form because gravity is stronger in low-density regions, causing matter to clump together more efficiently. So, the existence of the KBC void could be seen as evidence in favor of MOND. But MOND also has its own difficulties. It cannot fully explain the cosmic microwave background or the large-scale clustering of galaxies as seen in surveys like the Sloan Digital Sky Survey. The debate between LCDM and MOND continues, and the KBC void sits right in the middle of it. Now, let's turn to the Fermi Paradox. How does living in a void affect our chances of encountering extraterrestrial intelligence? The classic argument is that if the universe is teeming with civilizations, we should see some evidence of them, whether it's radio signals, probes, or megastructures. But if our galaxy is situated in a vast underdense region, then we are effectively isolated. The number of galaxies within the KBC void is lower than average, which means fewer stars and fewer potential habitable planets. Even if intelligent life is common in the universe, it might be concentrated in denser regions like the Virgo supercluster or the Great Attractor region. Our local group of galaxies might be a backwater. The distances to the nearest galaxies outside the void are enormous, on the order of hundreds of millions of light years. Any signals from those civilizations would take hundreds of millions of years to reach us, and we have only been listening for a few decades. Moreover, there is an even more speculative idea. Civilizations in denser regions might avoid expanding into voids because they are resource poor, or they might simply be unaware of our existence. The anthropic principle also plays a role here. Some have argued that we should not be surprised to find ourselves in a void, because voids provide a relatively safe environment for life to evolve. In denser regions, galaxies collide more often, supernovae are more frequent, and radiation levels are higher. A void offers a more stable, quiet corner of the universe, where life can emerge without being constantly disrupted by cosmic violence. So, our location in the KBC void might actually be a necessary condition for our existence. This is a version of the anthropic selection idea. We observe a low-density region because only in such a region could observers like us arise. But we need to be careful. The anthropic principle is often criticized as a philosophical cop-out, because it can explain almost anything by saying, if things were different, we wouldn't be here to observe them. Nevertheless, when combined with the empirical evidence for the KBC void, it offers a coherent narrative. We are in a bubble of relative emptiness, which explains both the Hubble tension and the silence of the cosmos. This does not mean the void is definitely the answer. Scientists are still gathering data. New surveys like the Dark Energy Spectroscopic Instrument, DESI, and the Euclid mission are mapping the distribution of galaxies with unprecedented precision. In the next few years, we will get a clearer picture of whether the KBC void is a true anomaly or just an artifact of biased samples. One important caveat: not all astronomers agree that the Milky Way is inside the KBC void. Some argue that the observed underdensity is a result of selection effects. Maybe we are just not seeing all the galaxies in that direction because of dust or other observational biases. Others point out that the evidence for the void relies heavily on the Tully-Fisher relation, which is not perfectly calibrated. There is also a rival idea called the dark flow hypothesis, which suggests that the bulk motion of galaxies is caused by the gravitational pull of structures beyond the observable universe, not by a local void. So, the debate is far from settled. The KBC void is a hypothesis, not a proven fact, but it is a hypothesis with strong observational support and profound implications. Let's step back for a moment and think about what it means to live in a cosmic void. The universe is unimaginably vast, and we are just a tiny speck on a planet orbiting an ordinary star in an ordinary galaxy. But if the KBC void is real, then our galaxy is even more ordinary than we thought. It is situated in a region that is emptier than average. That emptiness might be the reason we feel so alone. It might also be the reason we measure the universe to be expanding faster than it actually is. It might even be the reason our theories of gravity and dark matter seem to work so well locally but break down at larger scales. Ultimately, the KBC void is a reminder that our perspective is limited. We are embedded in the universe, not outside it, and our observations are inevitably biased by our location. As we refine our maps of the cosmos, we may discover that we are not at the center of anything special, except perhaps the center of a vast, quiet desert. And that might be the most profound discovery of all. The silence of the universe is not a sign that we are alone, but a sign that we are in a very quiet neighborhood. So the next time you look up at the night sky, think about the void. Those stars you see are mostly in our own galaxy, but beyond them, in every direction, lies an expanse so empty that it stretches for billions of light years. We are surrounded by emptiness, and that emptiness shapes everything we see, every measurement we make, and every search for other minds. It may be the most important thing about our cosmic address. We don't yet know if the KBC void will stand the test of time, it's a confirmed feature of the universe. But the story of its discovery, the controversy it sparked, and the solutions it offers show that science is alive and messy. The Hubble tension remains unresolved. The Fermi Paradox continues to haunt us, and the debate between LCDM and Mundi rages on. But one thing is clear: the universe is not as simple as we once thought, and that is exactly what makes it so fascinating. Now, if you've enjoyed this journey through the cosmic void, consider subscribing, Because the universe is full of mysteries, and we've only scratched the surface. From dark energy to the great attractor, from cosmic voids to multiverse theories, there's always more to explore. So stay curious and keep looking up. Because even if we are living in a bubble, it's a bubble that contains everything we know and love. And that's pretty amazing. Thanks for watching. And if you want to dive deeper into the science of voids and the Hubble tension, check out the links in the description for further reading. I'll see you in the next video. Before we wrap up, let's revisit what the KBC void actually means for our everyday understanding of the cosmos. We often think of the universe as a vast, evenly sprinkled collection of galaxies, like raisins in a perfectly mixed dough. But the KBC void suggests that the dough has giant bubbles, and we happen to be inside one. That's a humbling thought. It means our local patch of the universe is not representative of the whole, and that has consequences not just for cosmology, but for how we interpret every astronomical observation we make. Take, for example, the measurement of dark energy. The standard model of cosmology includes a mysterious force called dark energy that is supposedly causing the expansion of the universe to accelerate. That conclusion comes from observations of distant Type Ia supernovae in the 1990s, which won a Nobel Prize. But if we are inside a void, the apparent acceleration might be partly an illusion. The void could mimic the effects of dark energy on the expansion history. Some researchers have even proposed that we don't need dark energy at all if the void is deep enough and we are located close to its center. This is a radical idea, but it has been explored in papers using the timescape model, which argues that the universe expands at different rates in voids and in dense regions, and that our perception of acceleration is a result of averaging over these inhomogeneities. While the timescape model is not widely accepted, it shows that the void hypothesis forces us to question some of our most cherished assumptions. The KBC void also has implications for the cosmic microwave background. The CMB is a snapshot of the universe at 380,000 years old, and it is remarkably uniform. But if we are inside a large void, that void would leave an imprint on the CMB via the integrated Sachs-Wolf effect. As photons travel through the void, they gain energy when entering and lose energy when exiting. But due to the gravitational potential changing over time because of the expansion, there is a net shift. For a void as large as KBC, this effect should be detectable. And indeed, there are hints of a cold spot in the CMB in the direction of the Eridanus supervoid, which is a smaller void. The KBC void might contribute to a larger scale anomaly. So far, the data is inconclusive, but future CMB surveys like the Simons Observatory could help pin this down. Now, let's address the elephant in the room, the conflicting information about the Milky Way's location. You might have heard that we are on the outskirts of the Virgo supercluster, or that we are near the center of the Laniakea supercluster. These are different scales. The KBC void is a much larger structure, billions of light-years across, while the Laniakea supercluster is about 500 million light-years across. So, it's perfectly possible for the Milky Way to be both in a supercluster, a dense region on intermediate scales, and in a giant void, an underdense region on larger scales. Think of it like a foam. There are dense filaments and walls, but on the largest scales, even those filaments are part of a bigger bubble. Our galaxy sits in a relatively dense local filament, but that filament is embedded in a vast underdense region. That is precisely what the KBC void describes, a lower-than-average density on scales of hundreds of megaparsecs, even though our immediate neighborhood is normal. One of the most cited studies on the KBC void is the 2017 paper by Keenan, Barger, and Cowie. They used a sample of galaxies from the 2-micron all-sky survey, 2MASS, and the 2MASS redshift survey, 2MRS. They found that the number density of galaxies within 300 mpz is about 20% lower than the mean. They also noted that this underdensity is not isotropic. It is more pronounced in certain directions, which is consistent with a void that is slightly elongated. Subsequent work by other teams, using data from the Sloan Digital Sky Survey and the 60th Galaxy Survey, has generally supported this finding, although some studies have found a smaller underdensity of around 10 to 15%. The debate is ongoing, but the key point is that the existence of a significant underdensity in the local universe is now widely accepted. The question is its exact size and depth, and that brings us to the scientific standing of the KBC void. It is not yet a settled fact. Some cosmologists argue that the observed underdensity could be a selection effect. Maybe we are missing galaxies because of dust extinction, or because low-luminosity galaxies are harder to detect. Others point to the fact that the peculiar velocity of the local group, our galaxy and its neighbors, relative to the CMB, is about 600 kilometers, which is unusually large. If we are in a void, we would expect a large bulk flow toward the denser regions, and indeed, the observed peculiar velocity is consistent with that picture. But alternative explanations exist, such as the pull from a massive structure like the Shapley supercluster, or even the Great Attractor. The KBC void is just one piece of a complex puzzle. Perhaps the most exciting aspect of the KBC void is how it connects different mysteries. The Hubble tension, the Fermi Paradox, the large-scale bulk flows, the abundance of voids in simulations, all these threads come together if we accept that we live in an unusually empty region. This kind of cross-disciplinary synthesis is rare in science, and it makes the void hypothesis very attractive. But it also means that if the void is disproven, we will lose a unifying explanation and be left with multiple separate puzzles. So, what does the future hold? Over the next decade, surveys like DESI will map the positions of tens of millions of galaxies, giving us a three-dimensional map of the local universe with unprecedented detail. If the KBC void is real, we should see a clear signature, a spherical or ellipsoidal region where the galaxy density is low, surrounded by a denser shell. We should also see a coherent flow of galaxies away from the void center. These predictions can be tested. On the theoretical side, cosmologists are running new simulations with alternative gravity models to see if they can reproduce such a void without violating the CMB constraints. If MOND or other modified gravity theories can do it, then the existence of the KBC void becomes a strong argument for revising our standard model. But let's not get ahead of ourselves. The universe has a way of surprising us. Perhaps the KBC void will turn out to be a statistical fluctuation after all, a rare but not impossible event in LCDM. Or perhaps it will be confirmed, and we will have to accept that we live in a very special place, not special in the sense of being privileged, but special in the sense of being peculiar. That peculiarity could explain why we feel so isolated and why our measurements of the expansion rate are off. I want to leave you with a final thought. The idea that we are inside a cosmic void is not just a scientific curiosity, it's a profound shift in perspective. For centuries, humans believed they were at the center of the universe. Then Copernicus moved us to a planet orbiting the Sun. Then we learned the Sun is just one star among billions in the Milky Way. Then we discovered the Milky Way is just one galaxy among billions. Now, we are learning that even our galaxy's position is not average. It's in a desolate region, a cosmic backwater. That's a humbling progression. But it also gives us a unique vantage point. From inside the void, we can see the rest of the universe without the clutter of too many galaxies in our way. It's like being in a dark room with a clear view of the light outside. So the next time you feel small and insignificant, remember, you are not just a speck on a pale blue dot. You are a speck inside a bubble of emptiness that stretches for billions of light years, and from that bubble, you are trying to understand the whole cosmos. That's a remarkable thing. Keep asking questions, keep looking up, and maybe, just maybe, the void holds the answers we've been searching for all along. Thank you for watching. If you enjoyed this deep dive into the KBC void and its implications, please like and subscribe. It really helps the channel. And let me know in the comments. Do you think we are alone because we are in a void? Or is there another explanation for the great silence? I'll read your thoughts and discuss them in a future video. Until then, stay curious and keep exploring the cosmos from our quiet little corner of the universe. Until then, stay curious and keep exploring the cosmos from our quiet little corner of the universe. But let's push a little further into what this void means for our understanding of life itself. You see, if we are indeed inside a cosmic void, a region with fewer galaxies, fewer stars, fewer planets, then the sheer scarcity of habitable worlds within our immediate vicinity becomes a kind of selection filter. It's not just that we are far from other civilizations because the void is empty. It's that the very conditions that allowed intelligent life to emerge here might be tied to the void's existence. Some researchers have proposed that voids, being less dense, experience weaker tidal forces and fewer violent events like galaxy mergers or supernova blasts. That relative calm could provide a stable environment for planetary systems to evolve over billions of years without repeated cosmic catastrophes. In other words, the void might be a cradle for life, not a desert. Think about that. We may be living in a quiet, protected bubble, an oasis of stability in a universe that is otherwise chaotic and crowded with destructive events. That flips the Fermi Paradox on its head. Maybe it's not that we are isolated. Maybe we are privileged. The void gave us the time and space to develop, while civilizations in denser regions might get wiped out by gamma-ray bursts or gravitational disturbances before they ever reach the stage of spacefaring technology. If that's true, then the silence of the cosmos is not a sign of loneliness, but a sign of our good fortune. We are the lucky ones sitting in a cosmic sanctuary. Now, there is a darker twist to this idea. If the void is indeed protective, then stepping outside the void might be dangerous. As we send probes and signals farther into the universe, we are essentially shouting into a dense forest full of predators. The void's very emptiness might be why we haven't heard from anyone else. They might have learned to stay quiet in order to survive. That's a sobering thought, and it adds a whole new dimension to the search for extraterrestrial intelligence. Maybe the reason we haven't found anyone is that everyone who could broadcast has already been silenced by the very forces that our void shields us from. It's a hypothesis that pushes us to reconsider our own future. Should we be broadcasting our presence at all? Are we inviting trouble by sending messages into the denser regions beyond our local hole? These are questions that science fiction has explored for decades, but now cosmology gives them a concrete foundation. Our location inside the KBC void might be both a blessing and a curse. It allows us to exist, but it also blinds us to the dangers lurking just beyond our horizon. Let's also consider how the void affects our understanding of the universe's large-scale structure. The cosmic web, the network of filaments and voids that makes up the universe on its grandest scales, is a direct consequence of the initial density fluctuations after the Big Bang. In the Standard Model, small ripples grew over time under gravity to form the clumpy distribution we see today. The voids are the underdense regions that have been drained of matter by the gravitational pull of the filaments. But the KBC void is so large, about 2 billion light-years across, that it challenges the typical size distribution predicted by simulations. It's like finding a room in your house that is 10 times bigger than any other room, with almost no furniture inside. That anomaly suggests that the initial conditions in our local patch of the universe might have been different. Perhaps we are sitting in a region that experienced a rare extreme fluctuation, one that is statistically improbable but not impossible. And that improbability has deep implications for the Copernican principle, which states that our position in the universe is not special. If the KBC void is real and we are near its center, then our position is actually quite special. It would mean that the universe has a privileged observer, us, in a place that is far from average. That would be a revolution in cosmology comparable to the shift from a geocentric to a heliocentric model. We would no longer be just a typical observer. We would be an atypical observer, and that would force us to reconsider every statistical inference we make about the universe from our local sample. And here is another layer. If we are in such a large void, then the expansion rate we measure locally is not the true global expansion rate. As we discussed, the Hubble tension might be resolved by the void's gravitational effects, but that resolution comes at a cost. It means our measurements of dark energy, which rely on the assumption of homogeneity, could be fundamentally flawed. The entire edifice of modern cosmology, the lambda CDM model with its dark energy and dark matter,